Hey everybody, I'm Karissa, Stisser, Robotics Software Engineer, and today we're going to talk about really hard to debug things and how to make it easier. Let's say you're developing an algorithm, you need to test it on a robot or your embedded system, and the ideal situation, if it's going to crash, is it crashes with an error report or it's repeatable. Now that doesn't happen every time, so sometimes it can be confusing because it doesn't crash every single time, it's not repeatable, or you can't figure out the situation that it is going to crash, or you don't get an error report. It may even continue to crash every time, but you're not getting your error report, so you're not entirely sure what's going on. Now if this happens, you may try to think of what was the situation where it crashed or it failed, and you might try to hypothesize about maybe this was the reason why it happened, and then you go and develop a solution which may or may not be the cause to begin with, and then you go and test your solution and you don't see that error again. Well, do you know if you fixed it? I don't know. That can happen sometimes. Now, there are 9 different situations that I could think about that this might happen, and there are things that you can do to try to mitigate it to reduce the chance of wasting time. Some of the algorithms that I've worked on in systems are multi-target tracking, perception, SLAM. I've also done remote control and human-computer interfacing. So those are kind of the perspectives that I'll be coming from. Let's get into it. Number 8, memory usage. It can happen sometimes where maybe you have a memory leak in your algorithm and it just continually stores more and more and more information, and eventually your system just crashes. There's no error report, nothing in your log, unless you've explicitly written something, so you don't know what's going on. You need to dig in and try to figure out. If you're online monitoring what's going on, a really clear indication is if you bring up HTOP, you can look at the memory usage, and if you see it continuously increasing over time, you know there's probably a memory leak, or you're just storing an insane amount of data. Don't store all of your LiDAR data, that will kill you. You can also add this information in your logging to like a system health panel, and that'll make it a lot easier to be able to see in the end, okay, my memory keeps going up and up and up and up. Why is that in my algorithm? I need to go debug and use Valgrind. Number 7, extreme temperatures. You may have systems that are purposely meant for extreme weather and they'll be tested more. If you get into like medicine and biology, then you may need things at certain very low degree temperatures, and you may need automated systems to be able to manipulate those things, so you'll have a high amount of testing in that specific temperature range. But if you have an autonomous vehicle or autonomous delivery bot that's making deliveries most of the time in normal weather that you're used to, and then you start expanding out to situations where other people don't want to leave their house, like in the middle of a blizzard in Vermont, or in the middle of Texas in the middle of summer. If your system starts to abnormally fail, you may be suspicious of the temperature change that has happened. Having a lot of testing in that specific temperature range and a lot of data on how your system performs will help you with gaining confidence in how your system is able to perform in that kind of testing environment. The best thing you can do is either compile a lot of data based on your system running in that type of environment, or sometimes there are other ways to stress test your system. CubeSat radios, for example, will be sent out in low Earth orbit, and there will be a lot of vibration, there will be a lot of, what is the temperature at in low Earth orbit? Let me check. But you might get like a little box that can go to these extreme temperatures, and you'll set your system in it, and you'll have a certain number of hours, you'll record the data on how it performs in that type of environment, and that'll give you some type of confidence on how you expect your system to be able to run, to know that that change in temperature isn't actually the cause of a failure. Or maybe it is. Maybe you know that there's a certain type of reduction in accuracy or reduction in consistency. But doing that type of stress test is important for being able to have that knowledge of how your system works in different environments. Number 6, cable or sensor failure. Sensors and cables are not perfect. There are certain things that end up bending the cables and make it so that they might eventually break. There's wear and tear over time, sensors eventually fail, so you need to anticipate that this might happen. But it can be a back and forth if you don't have any hard data on if something's failing and you're suspicious that it might be the sensor. Is it the sensor or is it the algorithm? So how do you decide what's going on? This is where it's really helpful to have something in place in the software that monitors what's going on with your sensor output. And you can have an error message that says, okay, this sensor is running at an incorrect rate, or we've missed this amount of information in the sensor, and sometimes one blip in sensor information can cause a huge crash in your system. I've written a sensor confidence module before where you're able to tell both, do you consistently have information from your sensors? Are your sensors currently being blocked? Because that kind of information can be really useful and really helpful for being able to determine, is the information that your algorithm is producing actually of high confidence and you're able to act on it. Number 5, machine learning recognition failure. I keep going to autonomous vehicles, but that's because I worked on a delivery bot. Maybe you have an autonomous vehicle that is programmed to react differently to emergency systems, fire truck or police vehicle, so that if the lights are on, it won't go around it, it'll stop and pull over the side. But maybe you fail to do that, and so it's trying to recognize, why did you fail to do that? It doesn't recognize a certain type of fire truck or police vehicle because they look different, in many different locations. They're even different colors. You'll really want to be able to capture that information. Something that you can do to help is, if you're running a machine learning model on a system, you can have a trigger point to collect data, because a lot of times you won't be able to just store the whole bit of information just based on memory constraints. So LiDAR, you end up with like hundreds of gigs, and cameras a lot less memory, but still you may have constraints depending on the time your system's running. So you can have trigger points where if you know there's a failure, or if you're monitoring it and you want it to be able to capture a certain amount of information because something acted oddly, you may have it set up in your system so that it splash collects the last minute of what happened so that you can analyze it later. And if you're analyzing it later, you may be able to use that data and label that data to be able to enhance your machine learning model, because maybe it just didn't have that type of variation in the data. Number 4, CPU usage. In embedded devices, you have Android systems, you have augmented reality systems, you have watches, and these aren't all robots, but in embedded systems, you often get into computational resource restraints. You have larger robotic systems that also get into computational resource restraints, but it may just be because they're running insane algorithms where you need to track lots of things, where you need to run localization in SLAM and know where you are. So everything's fighting for CPU or GPU. It can happen where you have everything that's running, there's more and more and more CPU usage, and it's just too much and it crashes. And there's no clue, no indication as to what went wrong in your algorithm, so you don't know what brought the system down. Again, if you're running online, you can bring up HTOP and you can see how many of the cores are what percentage utilized. And you can actually see the top users on HTOP saying, this is the thread that's taking the most usage, this is the thread that's next. And that can be a good clear indication if you're running online. I've definitely crashed my laptop a number of times where I got like the blue screen of death when training a machine learning model. Yeah, that's computationally expensive. So what can help is you can add in logging reporting tools so that you can log how much CPU usage each thread is actually using while your system is running, and be cognizant of sometimes you have something that has like instantaneous spike, and then other times you just have longer term usage. So ultimately you need to bring down the top thing, whatever has those like highest peak values. You need to work on efficiency of an overall algorithm, and it may mean that you need to pinpoint like these instantaneous spikes that just bring down the system because it's too much all at one time. Maybe you can spread things out, maybe you can separate things into threads. You really need to, that's a whole nother topic for a whole nother video. Number 3, latency. Latency is just your system is not running fast enough. It may be that not enough information got to the place fast enough to be able to run the algorithm. It may be that the algorithm isn't fast enough to be able to get the result that you need. And this can get a little tricky because sometimes latency can be caused by CPU. If your CPU is overutilized, then you may not be able to perform all your processes fast enough. Adding enough logging information will definitely help you determine latency and be able to tell if your system is up to speed and it's running properly. It can really help visualize things if you're able to add plots, so that instead of just looking at timing information within your logs, you can see a nice graph, because you can much more quickly be able to see anomalies or be able to see a trend in what's going on with your algorithm. Number 2, timing. So if you're running a multi-target tracking algorithm, you're going to have camera, radar, LiDAR all coming into the same system. You need to make sure that they're synchronized and that the data that you're looking to associate to each other are close enough in time to make that association, because the reports that you're getting from the sensors may not be exactly at the same time. They're probably not going to be exactly at the same time. It also gets interesting because you may have, camera information where you're running segmentation, but that can only run at 5 Hertz, but then you're also getting LiDAR and radar, and that's running at 10 Hertz. But if you're running into a multi-target tracking system, you're maybe trying to associate one frame to the next frame to the next frame, and so you have to make sure that you're not giving double the same information to be able to keep it up at the same speed. You want to make sure that you're not giving double weight to the other sensors. You want to bring all of the information as you can and be able to combine that and have sensor fusion to be able to get your end result. So what can help for timing is if you have nice plots at the end of the system saying basically this happened at this time, this happened at this time, this happened at this time, and if you can see trends or if you can see alignment on the system had this issue at this time, this is what happened at that time, or this is what happened leading up to that time, then you may be able to make that better connection of that might be the cause. Number 1, calibration. Calibration is crucial for your system. So that's basically making sure that each of your sensors are aligned to each other. You know exactly where they are positionally based on the extrinsic information in relation to the center of the robot or the system. If this is off, it'll affect how you interpret the information that you're getting from your sensors. Tracking or SLAM will be off. And sometimes what can happen is your algorithm can have a high error and you don't know exactly why, and you have to go debug and figure out what is the cause. Is it the complexities of the probabilities of the algorithm, or could be machine learning algorithms that are less interpretable, but it could be at the very base level where it's just a calibration problem, and if you fix that, then that'll help the rest of your algorithm. There's surgical robotics where you have to have high precision. If you're working on an autonomous vehicle, then if your LiDAR is 1 degree off, then at 1 meter ahead, it'll be 0.3 inches off. It'll amplify the further you get it away. So if you're looking across an intersection about 6 meters away, then you're going to be about 2 inches off. And that's going to increase the farther you get. So if you're going in high speed traffic, everything matters. And you need to both have accurate localization so that you know exactly where you are, as well as accurate tracking so that you can make sure you're not going to run into anything around you. Yes, I'm using meters and inches because I'm an American engineer. A clue that it can be a calibration issue is that it's just happening on one system, one robot, and then the rest of the robots are fine. But really you want to get a more accurate answer as to say this is the issue. There can likely be maybe 3 different steps of checking your calibration, which you can do this to help give you that definitive answer that calibration is the issue. One would just be taking the logs and looking between 2 different LiDARs, aligning them to make sure that the respective calibration between these 2 sensors are correct. That's like the down and dirty version. Another would be you really want to have continuous checks for your systems to make sure that calibration is aligned. So for instance, maybe at the start of the day or at the start of each run, you can have a set environment where you anticipate needing to have something in a certain space. You bring it up, you do that check that whatever is in your space is correct, and then you're able to do your run with high confidence that your calibration system is correct. And maybe there's a log report, based on the calibration information, so that when you're looking at the log data later on after you've run your algorithms, you can look back and see, okay, this is the state of the calibration system. I know that's not the issue, or oh boy, this doesn't look so good, so I better look more into that. Maybe on bring up, you're looking on if you have sensor overlap, then you can see, okay, I know these features should be within the space. If I have very low matching between these features, or it seems like the features are matched but there's some shift between the location of the sensors, then you know there might be an issue. Another way to do it would be an online check, so maybe periodically you would be able to run a check to say, okay, do my sensors seem aligned? Now the challenge with this is it takes up CPU, so if you're already CPU challenged, then you may not be able to run something online because it's taking CPU away from something else. But again, you can check and see, all right, this is the overlap that I know my sensor should have, and what are the features between the overlap? Do they align, or is there a misalignment between the location of those features and the location of the sensors that we know? And finally, number 0, because I'm a computer science nerd, use case failure. So previously, when I was talking about difficult to debug system, it was more of like, okay, something crashed and you don't know what went wrong, and so you have to figure out what went wrong to try to debug and try to fix it. In this scenario, I'm talking more about, all right, you know what went wrong, but because of failure of understanding the situation and the whole application, once you get to the point where it's being used, you recognize, oh, this is what went wrong. I didn't anticipate this type of situation, or I didn't completely understand the scenario in which my robot or system is going to be used. So now I have to like re-architect code, and there has to be a big change in the system. An example might be for like a small aircraft. Maybe it can't just sit on waiting to be able to go move. So the startup time for whatever system has to be running on that aircraft needs to be short enough so that once it starts up and it goes out, it's up and running as soon as possible. There may be too many barriers between the engineer and the user or the person you're selling it to. So you have like the salespeople and the business people, you have the managers, you have the engineers, and sometimes there's a few barriers in between for the person that's actually implementing the solution. But to be able to solve this type of thing, you really want to both have as few barriers between communication from the engineer to the end user as possible. You want to develop and test quickly and test often, so that if something fails, you know that it fails earlier on and you're able to change and adapt to it without having to change too much code. The other thing that can actually also do this is the human-computer interface element, which you may think you have a good solution, but once you actually test it with other people, what might be intuitive to you is not intuitive to somebody else. You have a situation where you have an autonomous vehicle that's moving to a stop at an intersection. Oftentimes there would be, if two people come to the stop at the same time, you have that awkward like, all right, who stopped first? And then you have that like head nod or the hand wave that says, all right, you go ahead. Or maybe they both do that, and then one of the people goes, okay, thanks, and they go ahead. And that resolves that. But how does an autonomous vehicle do that? Maybe they have lights that indicate, okay, I'm about to go, so that it helps avoid collision. When I was developing an augmented reality app a few years back, so it wasn't quite intuitive to say, all right, what do you do to be able to like zoom or interact with this thing in space? So you zoom with a phone like that, so do you do the same thing? But you do the same thing when you're like selecting things, and you look really weird when you like got hands all moving up in space. But so it may even be to come to a solution, just ask questions to people around you, like as long as you're able to. Say, if you were doing this, like would this seem natural to you? Or maybe even run a test without developing anything. Have somebody in a situation and say, if you wanted to be able to do this, does this feel natural? If someone did this, what would you think that they were doing? And try to get some information and data to then develop a better system and a more intuitive system. And if something isn't working, you may need to change it. This comes from many hours of programming and debugging and learning from systems, so I hope it was helpful to you guys. If you like what I made, consider liking and subscribing, and we'll see you next time.